Welcome to the presentation on minimum operations to exit threshold value, the second problem. In this session, we will walk through the problem breakdown, approach, and the solution to determine the minimum number of operations needed for a given integer array. Our objective is to find the minimum number of operations required to make all elements in an array greater than or equal to a given integer k. The allowed operation is as follows. We select the two smallest integers from the array, remove them, and insert a new number, calculated as min x, y times 2 plus max x, y, back into the array. We repeat this operation until all elements are greater than or equal to k. Let's take a look at example 1. We have the array with elements 2, 11, 10, 1, 3, and k equals to 10. The goal is to make all elements greater than or equal to 10. In the first operation, we remove the two smallest numbers 1 and 2. The new number we insert is 1 into 2 plus 2, which equals 4. The array now becomes 4, 11, 10, 3. In the second operation, we remove the two smallest numbers 3 and 4. The new number we insert is 3 times 2 plus 4, which equals 10. The array now becomes 10, 11, 10. Now all elements are greater than or equal to 10. The answer is two operations. Now let's look at example 2, where the array is 1, 1, 2, 4, 9, and k equals to 20. In the first operation, we remove 1 and 1, and the new number we insert is 1 times 2 plus 1, which equals 3. The array becomes 2, 4, 9, 3. In the second operation, we remove 2 and 3, and the new number is 2 times 2 plus 3, which equals 7. The array becomes 7, 4, 9. In the third operation, we remove 4 and 7, and the new number is 4 times 2 plus 7, which equals 15. The array becomes 15, 9. In the fourth operation, we remove 9 and 15, and the new number is 9 times 2 plus 15, which equals 33. The array now becomes 33. Now all elements are greater than or equal to 20. The answer is 4 operations. To solve this problem, we use a min heap, also known as a priority queue. This data structure allows us to efficiently retrieve the smallest two elements from the array. We follow these steps. Push all elements from the array into the priority queue. Continuously extract the two smallest elements, apply the operation, and insert the result back into the queue. Keep track of the number of operations performed. Stop when the smallest element in the heap is greater than or equal to k. Now let's look at the code implementation. In part 1, we first define the function and initialize a priority queue. We insert all elements from the array into the queue. This allows us to retrieve the smallest elements efficiently. In part 2 of the code, we continuously perform the operation until the smallest element in the heap is greater than or equal to k. We extract the two smallest elements, apply the operation, and push the result back into the priority queue. Each time this operation is performed, we increment the operation count. Finally, we return the total number of operations. Now let's discuss the time complexity. The time complexity of this approach is big O of n log n. Pushing elements into the priority queue takes big O of log n time for each element. Each operation, which involves removing two elements and inserting one, also takes big O of log n times. Hence, the overall time complexity is dominated by the priority queue operations. The space complexity of this solution is big O of n. This is because the primary space usage comes from storing the elements in the priority queue. In conclusion, using a priority queue allows us to efficiently manage and retrieve the smallest elements in the array. This approach guarantees the minimum number of operations needed to ensure all elements in the array are greater than or equal to the given threshold value k. That brings us to the end of the presentation. I now open the floor for any questions or discussion. Thank you for your attention.